we're being asked to find the linear equation tangent line to the function that we've been given here. So it's a good idea to know what this function looks like. So I'm just going to sketch a graph of this function. It has a vertical asymptote at x equals 1/2. Okay, it's got a horizontal asymptote, and it looks like it's going to kind of pass through there. So we've got a graph that kind of looks like that, and it's going to go like that. So at x equals 1 and x equals 1 and x equals 0. So x equals 0 is here. At x equals 1, it looks like there's some point over here somewhere. Okay, we're going to find the tangent lines at those points. Okay, so I'm going to do x equals 1 in blue. Okay, so we're trying to find the equation of that line. To do that, we need the derivative. So we need f prime. Okay, so f prime, we're going to apply the quotient rule. There is something called the reciprocal rule as well, but I'm just going to apply the quotient rule here. So we're going to end up with it's going to be 2. Well, we'll do the first part here. So the derivative of the first part is 0 minus 2 times the derivative of the denominator is -2 divided by 1 minus 2x all squared. Okay, so simplifying this, I end up with 4 over 1 minus 2x all squared. So there's my derivative function. I'm going to use that derivative function to calculate a slope value at x equals 1. Okay, the slope value, that's going to be x equals 0. When I plug in 0 into my slope function, I get a slope of 4. And the y value at 0, okay, when I plug in 0 into that equation, I'm going to end up with y equals 2. So I have my slope is 4, my coordinate is 0, 2, so plugging it into the point slope formula, I'm going to end up with an equation that looks like this. So that's going to be 4x plus 2, so that y equals, this line here, the blue line, has a slope of 4. The point at x equals 1, we're going to have a tangent line here. So at x equals 1, we need to calculate the slope at 1. So plugging into my slope formula here, I end up with, looks like 1 minus 2 squared. So it's going to be, has the same slope of 4. So it is symmetrical across that point. So it's going to have symmetrical slope. Okay, and f of 1, when I plug 1 into my original equation, okay, so I'm going to end up with 2 minus 2. So 2 over 1 minus 2, which is -1. So I get a y coordinate of -2. So then plugging that into my point slope formula, I get x minus 1 minus 2. So there's the tangent line to that coordinate there. Okay, so there's a red tangent line. So, and again, just notice that I leave it in point slope form. That's far more efficient and easier to work with than trying to put it into y equals mx plus b. We have the slope, we have the coordinate, point slope form is good enough. Okay, so there's my 2 tangent lines there. The last part of this here is just relating the shapes of the graph to the derivative, the original function, and the second derivative, or in this case, the velocity, position, and acceleration. So the key to this problem here is to recognize that there is a 0 here that relates to a horizontal tangent here. Okay, so what that means then is the blue function has a y coordinate of 0, where the slope of the green function is 0. That implies that the blue function must be the derivative function of the green function. So either the green is the position and the blue is velocity, or the green is the velocity and the blue is the acceleration. Okay, so let's just verify that first, that the blue is the derivative of the green. And if we take a look at the slope of the green, that's all positive through here. Okay, that matches. So that is consistent. I'll just do that in a slightly different color. Do that in a different color. So the positive slope here matches the positive y coordinates all through there. The negative slope here going down matches all the negative y coordinates here. Okay, so that's consistent. Okay, so we have this consistency of the slopes. So we can see, and the pattern of the slopes does match as well, because as the velocity or the derivative is getting flatter, here it's getting closer to 0. Okay, this is flattening out to 0. The derivative is flattening out to 0. Okay. So what we can say that is b prime is equal to the a function. Okay. So we just have to determine, is c the derivative of a, or is it the antiderivative of b? Okay, so if I take a look at c here, c is always increasing. Okay, so the derivative of this must always be positive. And it starts kind of low. It starts with a slope of 0, and it increases, and it goes back to a slope of 0. Well, b follows that type of pattern. It's always positive. Okay, it's always increasing. It speeds up, and it slows down. So that implies then that b must be the derivative of c. Okay, so c prime is equal to the b function. Okay, so that means that the c function must be, do I have a pink here? I think I have a pink. The c function, I'll just keep it in red. C represents the position function. The derivative of position is velocity, so then the b function, b must be velocity. And then a is the derivative of b, so the a function must be the acceleration. Again, there's lots of different ways to do this. However, there is a key part here where we can match the horizontal tangent with a 0 position, and that means that we can make the conclusion, well, not a conclusion, but we can infer that the a must be the derivative of b, and that's a good starting point.